Hi, my name is Yuri Habits and I'm an engineer at Unity. Together with Ben Clark from ARM, we are going to talk today about mobile performance and using ARM Neon instruction set with the Unity Burst compiler. Before we start, I'd like to briefly introduce Unity in case you have only briefly heard about us. Unity is the world's leading platform for creating and operating interactive real-time 3D content. Our platform provides a comprehensive set of software solutions to create and operate content for mobile phones, tablets, PCs, consoles, and augmented and virtual reality devices. Unity is a company born from gaming. Our Create tools are responsible for some of the world's most popular games, and we are proud to say that games made with Unity accounted for 71% of the top 1,000 mobile games in Q4 of 2020. In the first 9 months of 2020, we saw an average of more than 5 billion downloads per month of applications made with Unity. Okay, now that we know each other, I'd like to briefly outline our today's talk goal. First of all, we are going to focus on CPU performance of Unity games. However, the techniques discussed today apply to non-game Unity apps too. We want our users to satisfy their creativity needs and meet the frame time deadlines, like 16 milliseconds for 60 frames per second. And once you cope with that task, further improvements may reduce the energy consumption, which is great for everyone. We're going to target mobile platforms today, I mean Android, which I have the joy and sorrow to work on for quite a few years. The Unity Burst compiler is the core part of the talk. And we're going to do a small dive into Neon assembly, of course with comprehensive explanations. We are proud to be working with the team at ARM to bring better mobile performance to all Unity creators. Our partnership centers around 3 key areas. First, we have core engine performance. This speaks to our work on the Burst compiler, which we're discussing today. Second, we have our performance optimizations for Unity's universal render pipeline, which unlocks mobile performance for multi-GPUs. And finally, we have our work on profiling with ARM, bringing additional profiling tools to Android developers so that they can more quickly identify performance drop-offs in their games. But before we proceed into more advanced topics, let me explain what the Unity Burst compiler is. Unity provides the users a range of ways to program the logic of their games, from visual scripting interfaces which require zero actual coding to low-level close-to-the-metal APIs for fine-tuning the performance of your game. The core language of the Unity universe is C#, which normally gets through a .NET compiler and outputs managed assemblies. However, with Burst, your C# code gets through several stages and then ends up in the LLVM backend, which outputs a native binary. It is already expected to be much more performant than a managed counterpart, but with Burst's knowledge of Unity internals, the result is much better than if using LLVM. Burst is a part of performance by default principle, making your C# code run blazingly fast with minimal effort. To show you the benefits that the Burst compiler is bringing to your project, I'd like to demonstrate you the video of a game demo with 3 playgrounds using Unity Physics, a stateless lightweight engine written in C#. We selected Unity Physics as a core demo component because it is math-heavy and naturally benefits greatly from Burst and vectorized code. There are 2 versions, one with Burst enabled, another with Burst disabled, and it runs on an Android phone. The camera and the interactions are scripted so no one touches the screen. And you can see that the difference in the frame time is at least 2x, with Burst being faster obviously. And please make note that quite some rendering is happening here, which is not CPU heavy. In a thermally throttled state, the difference stays about the same, but I must say that it takes much longer for the Bursted demo to make a device to start to throttle. As you can see, in some scenes the difference comes up to 4x. That's outstanding results, which makes for an easy win to adopt Burst in your game. So you were able to see the fantastic performance benefits that Burst brings you with minimal effort. The performance of Bursted output code is enough to satisfy 99% of the users. However, if you are within the remaining 1% who are still unhappy with the results and want to squeeze every extra CPU cycle out of your code, then we have a solution for you, and it is Neon Intrinsics. Neon Intrinsics are a way to write assembly code without actually writing assembly code. There is a one-to-one mapping of the API to CPU instruction, but no need for non-exciting things like register allocation, integration, and so on. The C# API is very similar to C API for easier use, and the ARM v8 intrinsics are available in burst 1.5, and support for more intrinsics including ARM v8.2 extensions is out in September with burst 1.6, so you are free to check it out right now. Okay, enough of theory, now let's jump onto the practical part. Let's start with something really simple like a dot product. Here is a short snippet of C# code I've written for you. Please don't pay attention to the trials outer loop here. It is there to make sure the calculation takes at least some measurable time. Now let's write a C# intrinsic implementation. If you have any experience with C intrinsics, you immediately see that it's familiar to you because the API and even the syntax is very similar. What we see here is two load instructions from the input arrays into vector registers, then comes a calculation, and finally we advance the pointers in the input arrays. You can process 4 elements in a single loop iteration, classics of CMD. If the number of iterations is not a multiple of 4, we have to calculate the so-called tail of up to 3 elements. You immediately see that there is more code here than in the managed version. Now let's build it onto an Android device and check the results. What do we see here? Managed result is there just for reference. It's an IL to CPP build, so it is native code that has gone through Clang. It is not mono-JIT, and it takes 387 milliseconds. Bursted version takes 82 milliseconds to complete, while the Neon Intrinsics version takes 119 milliseconds. The reference device here and further is a Samsung Galaxy S21, the European version with Exynos. The code is run single-threaded on the largest Cortex X1 core. So we see that the handwritten routine using Neon Intrinsics is slower than the code generated by the burst compiler. Why is that happening? Let's check the assembly in the burst inspector. If you're not familiar with the burst inspector, I highly recommend it to you as the ultimate diagnostics tool, which helps you check the assembly output for each of your bursted functions without having to build anything. Another cool feature is matching of C# source lines to assembly. Here is the assembly for the Neon code on the top, and the assembly for the managed version of the code that went through the burst compiler is on the bottom. Let's take a closer look at the Neon version. We see 2 loads and the calculation instruction. So what is in the assembly is absolutely equivalent to what we've written in C#. The burst compiler is auto-vectorizing the code, but it's doing it smarter than a simple Neon Intrinsics implementation because the loops are unrolled. What it means is that you have the loads and 2 calculation instructions in the loop, so one iteration processes 8 elements instead of 4. To understand why the bursted code is faster, let's take a look at what the CPU is capable of. Here is a screenshot from the Cortex X1 software optimization guide from developer.arm.com. Here are the load instruction variants used in the assembly above. As you can see, they have same latency and throughput, but LDP loads 2 registers, so it's immediately more efficient. SMLAL allows for 2 instructions per cycle issue with a 4 cycles latency, but there is an accumulator fast path for integers which allows for a 1 cycle latency. Yes, it's quite a hard job even with this data to understand how many cycles will the loop take on the CPU, but it apparently looks like issuing more instructions results in better performance. And I'm going to remind you once again that measuring is a fundamental part of any optimization. Okay, lesson learned. Handwriting simple Neon code doesn't necessarily mean it will perform better than what Burst generates for you by default. One of the reasons for that is that Burst did loop unrolling because it knew that the architecture of the modern CPUs allows for parallel execution, so it can handle more loads and more calculations at the same time. Let's try to beat the Burst compiler this time. And here are the suggested options. First of all, let's try unrolling the loops even more than Burst did. Second, let's use smlol2, which is a complementary instruction to smlol and operates on the upper half of the vector. I'm going to explain it in detail a bit later. And finally, let's try smlol2 and more unrolling. All the code is available on GitHub, and instead let's dive into the burst inspector assembly. This is one of the variants with more unrolling. In this case, it's 4x unrolling. 3x and 6x variants are pretty much similar. What we can see here are the full load instructions and for calculation instructions. This is my favorite assembly variant, short and elegant. It makes use of smlol and smlol2 instructions. First, it loads into Q2 and Q3 registers, which is the same as the CMD V2 and V3 registers. And then come the calculations. The smlol variant we were using is taking 4 shorts in the lower half of the 128-bit vector register as each input argument, and returns 4 ends in a 128-bit register as a result. However, if we load 128 bits from the input arrays, then we can use the smlol2 instruction with the same V2 and V3 registers as input, but calculate the upper half of the vector. This way we can use the loaded data even more efficiently and not ignore the upper 64 bits loaded anyway. This is similar to the previous smlol and smlol2 variant, but it is too wide unrolled. First change is that it is using LDP load instructions which load 2 Q registers at the same time from consequent memory address. Secondly, it uses 4 calculation instructions per iteration, allowing for 16 elements processed with a single loop iteration. Let's check the manual once again. In addition to the instructions you've already seen, I'm adding LDP Q form here, which loads 2 128-bit registers at once and has the same latency as the other load instructions. So we're able to have 256 bits of data loaded after 6 CPU cycles. And looks like it's the fastest we can get on loads. Now let's run on an Android device and see what we can get. The more unrolled variants are at least as performant as bursted code, and that's great. I tried it out on a few phones, and I must say the performance of the unrolled options varies from device to device, so use it with caution. The short and elegant smlol2 variant has about the same performance, and the too wide unrolled smlol2 variant takes only 66 milliseconds to complete. It is about 20% faster than what burst has to offer. Fantastic. Okay, so we just realized that burst is doing a really great job. We've written 7 new Intrinsics implementation variants in C#, and one of them was 20% faster than bursted code. Great result. However, the remaining 6 had performance same as burst or even worse, so some effort and experience is needed to write efficient Neon code, even for a simplest example. But the effort is worth it. 20% improvement on .prod is a great result brought to you by using C# Neon Intrinsics. What I wanted to say is don't hesitate to consult the manuals to better understand what's going on, and of course measure, measure, and measure again. Now on to Ben, who will look into a practical example a bit more complicated than just .prod.
Thanks, Yuri. And indeed, we will see that getting Neon faster than the compiler first time is hard. Let's look at my example. My remit was looking for a realistic game-like Android example that would benefit from vectorization with Neon, something that wasn't too complex, so the lessons could be general and learnt from. Once running, I could see how much difference I got moving good code to burst, and how much more performance I could squeeze out with Neon. I decided physics collisions would fit the bill if I made sure there were enough objects to test against each other. So I set up a scene to spawn lots of characters to randomly move about in a maze and test everything against everything. Our final trials used 2,400 characters and 236 walls. There are 2 different collision types within the project, giving me 2 different cases to optimize. For characters being tested against walls, I use axis-aligned bounding boxes. And for testing characters against other characters, I test based on the radius and position of the 2 characters. And there are 3 different implementations of each to compare. For the control case, I start with good, tight logic, but don't use burst. Then I wrap that in burst. Then I convert to using neon intrinsics within burst. For reference, there is a document that covers a lot of the same material as this talk. Link is just over here. And the code and scene from this example is on the Unity Asset Store. Link is just here. And here we can see the beautiful graphics in that scene. Sorry. As it's physics collisions, I just have the physics structures. There is no fancy rendering. The process where you'll be adding neon intrinsics in is going to be part of the measure optimize cycle, where you're trying to improve the performance of your game. You profile the game, identify the parts of the code that need better performance because the CPU is doing too much work, and try to improve them. Profile again, see what difference you made, and go around the cycle again as many times as needed. You need to make sure you do your profiling on the target device. For Neon, you need to run on Android for it to work anyway, but in general, you'll get different timings as you use different toolchains for the build, different hardware, different optimization settings, etc. What is a gain in one isn't guaranteed to be in another. The editor in particular, while great for debugging, has minimal optimization, a different toolchain, and so on, so it is pointless for profiling. Speedups there don't always translate to speedups in the final version. Burst jobs are great, with their asynchronous nature being helpful in a multi-threaded game. So when I started my project, I used burst jobs. But I found they weren't easy for my measuring. I've since discovered that there are good tools that can be used alongside them. Profiler marker can be passed in to then be used with profiler recorder and or profile analyzer to time within jobs. But as I wasn't making a game, so the asynchronous benefits of jobs weren't needed, and I wanted to display the timings on screen in my demo, I moved to a burst static function. Burst static functions are another great way to use burst, but are a bit more restrictive with the parameters they take. Just simple types, pointers to simple types, and references to structs that just contain pointers to simple types. This meant I ended up moving to pointers and changing the layout of my data when I changed to a burst static function, which means the function isn't as nicely just burst wrapped normal code, and does probably make it easier for the compiler to auto-vectorize, but that's a good thing. Which brings us to look more at auto-vectorization. This is what makes burst so good and what gives our handcrafted Neon a challenge. When targeting ARM64 as needed for Neon, you have to use Unity's IL2CPP toolchain. This toolchain, after converting to C++, uses Clang to compile, and Clang is now very good at auto-vectorization to Neon. But burst then improves on this, an easy performance gain. But there are things we can do in the code to help that auto-vectorization, setting up our data and loops so that they are simpler to then turn into SIMD commands. I've got a short list of useful rules here, but to take you through an example, looking at this radius-based collision detection code. For data, x, y, and radius are split up and treated separately, which allows each of them to be vectorized more easily. For loop structure, there are two short for loops with simple addressing, no indirection, no breaks in the loops, and it has an inline function. Lastly, I cannot stress the importance of the no alias attribute enough to let the compiler know that the data the pointers point to is not overlapping. We struggled as to why burst wasn't doing a good enough job until this was spotted. This small change meant it suddenly auto-vectorized and resulted in the radius code running in 1/3 the time it was, and the axis-aligned bounding box code running in 1/4 the time. Suddenly, burst was faster than some of my Neon, and I had to tune it some more. So, you've got burst implemented, and you can see in the burst inspector that it auto-vectorizes. What if it's still not efficient enough? Well, then we can look to write our own Neon. Likely this involves some loop unrolling, hence the title. But what do we need to look at when we go to make our own efficient neon intrinsics calls. Once again, data structure is important, as it is for auto-vectorization. Here, as you write the intrinsics yourself, you may get more ideas of what structure works best, so tweak as needed. Then, you have 3 phases. First, load efficiently into the neon structures. Likely it involves a VLD vector load function. Secondly, keep the data in vectors as long as possible. Don't go in and out of neon. Work out doing all the processing on multiple data rather than going back to single items. Thirdly, you want to store it efficiently. Unfortunately, the VST vector store functions didn't make it into burst 1.5, but Yuri's got them in as experimental in 1.6, so you can try them now. In the example, there are some pointer tricks to get things out efficiently, and I advise looking at the demo code for what's been done to extract as well as possible. The change in how I got the data out made quite a difference to performance, so it is important. Let's look at each of the 2 subcases to go through the important improvements. Starting with the simpler one, radius-based collision detection. Firstly, as before, we split the x, y, and radius for processing separately, so they're each able to have 4 loaded into a vector at once. Now neon code is quite long, especially the tail code for the less vectorized parts left at the end. So this is just a clip of the code on the slide, just the main inner loop. To see the full implementation, please get the example seen from the Unity Asset Store. So here we have one character already loaded in to compare against, and we loop through the other characters. We load 2 lots of 4 more characters at once, so we can do the comparison with 4 32-bit floats, but then compress the answers to 8-bit values, and then extract all 8 results at once into our Boolean array of collisions. This float to Boolean conversion is slightly easier in C# than C neon intrinsics, with Unity making good use of the dynamic typing to help us. The logic of the collision detection is exactly the same as in burst on slide 27, albeit a lot longer, as the x subtraction, y subtraction, result squaring, adding, and comparing to the squared radius are now all separate lines. We're just explicitly loading and comparing 4 at once, doing it again with another 4, and then squashing all the results with a table lookup into a shorter 64-bit vector so it's ready for extraction. As mentioned, we also have to cope with tail code, as the unrolling uses a multiple of 8, and we aren't guaranteed our number of characters will be a multiple of 8. So there is firstly tail code to cope if there's another 4 more, essentially similar to the first half of this, but with a slightly different extraction to get 4. And then more tail code for if there's fewer than 4 comparisons left for the character. I still load 4 in and calculate and redo some results because it will be faster than doing on average 2 singly. The more complicated case was the axis-aligned bounding box collisions. Here there was more potential to lay out the data well for neon and get a bigger advantage. As implemented in the original non-burst code, our best way to check for a collision is to check that the bounding boxes are not missing each other on each axis. If the maximum value of one is less than the minimum value of the other, then it's a miss. Repeat for both sides and each axis. If there are no misses, then it's a collision. But we can set up the data so that all the checks for a 2D collision can be one greater than check, with the neon doing all 4 checks in one command. For the first go, we do this, or the answers in another command and negate it to get the result, which gets some impressive performance and needs no tailcode, but we can do better. We can unroll our loop and do 4 walls at once. We do each of the checks for 4 walls and then can combine our results, meaning our OR and NOT do 4 walls as well, instead of 1 in the first version. And then we can do even better by doing the same extraction technique we did with the radius and doing 2 groups of 4 and then combining. Our NOT is now on 8 walls at once and extracting all the results in one go. Initially, I did the compression from 32-bit values to 8-bit ones with some bit shifts, but a table lookup allows it to be done in 2 instructions instead of 3, making a small further saving. As one final addition, we can remove some tailcode as our final test has a guaranteed number of walls. It's a multiple of 4, but not 8, so I just handle the case of the last 4 walls at the end. To have a quick look at the code snippet here, we load the character's 4 bounding box limits with VDUPs to put the same value into the vector 4 times, ready for comparison with 4 different walls. Then for each set of 8 walls, we handle 4 at a time and load 4 walls into each of 4 arrays representing each bound of the box. Then we're comparing the max of one to the min of another. Half the bounds are negated so that they all end up as greater thans. Not strictly needed in this final implementation, we could have less thans, but no slower either, as the negation is done once at data setup when loading. Grooming the data at setup like this can be important to your efficiency. The results of the 4 arrays are ORed together, giving us 4 collision results. They are then put into one end of a vector, ready for the next 4 results to be put into the other. Not seen here, those next 4 walls having been put in the other end, the whole lot is negated and extracted with a pointer cast like the radius-based collision detection code we just saw. Which brings us to our results. These are on a Galaxy S10 Plus, but a quick test on the S21 gave similar results. As you can see, Burst's auto-vectorization gives us some big speedups, especially for the axis-aligned bounding box case. Here it's running the collision tests in approximately 1/6 of the time that our tight, non-burst implementation takes. Neon Intrinsics allows us to shave off a further 40% of the time remaining. For radius-based, it's a simpler calculation and harder to get as much speed up, but still the burst implementation takes a little over 1/3 of the time of our original implementation, and Neon takes off another 20%. So these are some big gains. Burst gives us a big speed up without the effort of handcrafting Neon and the harder to read code. But if it's important and you need that extra bit of performance on Android, you can squeeze out some more with the Neon Intrinsics. So, to summarize, Burst is performance by default, easy to turn on for sections of your code, and it gives a big speed up with a lot of auto-vectorization. For 99% of users, this is all that's needed. But if you need to squeeze out more on Android, you now have C# Neon Intrinsics. Here you can fine-tune performance and get even better results. But to get those better results, you'll need to work hard to beat the compiler, so pick your battles of where you can get the performance gain for the time you spend implementing. As ever, when going for performance, profile to find where you can get your gains. Hopefully, the tips we've gone through on data layout and loop unrolling will help you get that ultra-efficient code you're looking for. We look forward to seeing that high-performance code in your new games. From Yuri and me, thank you.